Detecting dynamic objects and predicting static road information such as drivable areas and ground heights are crucial for safe autonomous driving. Previous works, especially those using deep learning, focused on improving each perception task separately, with task-specific network architectures and evaluation matrix. This task-specific solution is inefficient when dealing with multiple tasks and lacks a collective quantitative analysis. In this paper, we try to answer the question, can we jointly perform multiple perception tasks via a unified network architecture accurately and efficiently? In this regard, we propose LidarMTL, a multitask network which takes raw LiDAR scan as input and jointly performs 6 perception tasks for 3D object detection and road understanding. Here, objects are detected with class labels and 3D bounding boxes. The associated LiDAR points to objects are classified as foreground, and their relative locations to object centroids are regressed, which we call intra-object point location. In addition, the network predicts road information with point-wise drivable area classification, ground area classification, as well as ground height regression. Our network is designed for simplicity and efficiency. It is based on an encoder-decoder architecture with 3D sparse convolution and deconvolution operations. We have conducted extensive experiments to verify the proposed method. The resulting model is small, with only 6.5 million trainable parameters, and it runs at an inference speed of 30 frames per second on a Titan RTX GPU. It also achieves competitive accuracies compared to state-of-the-art object detectors and other task-specific networks. Finally, the network is leveraged for online localization. Code and the pre-trained model has been made available. This figure shows the proposed network architecture. In principle, LidarMTL works by adding task-specific heads to a 3D unit architecture and training the full network with a multitask loss in an end-to-end manner. The voxelized LiDAR points are fed into a unit backbone with the encoder-decoder architecture, which directly processes LiDAR points in the 3D space. The encoder consists of several 3D sparse convolutions and downsamples the input spatial resolution by 8 times in order to extract high-level LiDAR features. The decoder gradually upsamples the LiDAR features to the original spatial resolution via 3D sparse deconvolutions. We choose the unit backbone network and voxelized LiDAR representation because it well preserves the geometric information of LiDAR points by setting the proper voxel size. The unit backbone has been also shown in several works, such as w.r.t, to achieve higher efficiency than a raw point-based methods. For each pointwise prediction, such as foreground classification and ground height regression, a task-specific output layer is directly appended on the last feature maps from the decoder network. As for 3D object detection, we first project the 3D LiDAR features from the unit 3D encoder to the bird's eye view and process the bird's eye view features through several 2D convolution blocks. This network architecture design has been found more accurate than performing pointwise object detection from the unit decoder. The full network is trained end-to-end by an uncertainty-aware multitask loss. It uses the task-dependent uncertainty parametrized by the noise parameter sigma square to balance the single task loss. Such noise parameters are jointly optimized during training. The proposed method is verified using the Algoverse dataset with 3 groups of experiments. First, we compare LidarMTL with task-specific network regarding efficiency and accuracy. Second, we conduct several ablation studies to verify the network architecture design. Finally, we leverage LidarMTL for online localization. The following 2 figures show the reduced memory footprints and higher inference speed brought by LidarMTL compared to performing each perception task separately. When increasing the number of tasks, which is shown on the horizontal axis, the LidarMTL network remains constant model size and inference speed, while the single task model approach requires linearly increasing memory and much lower inference speed. When performing all 6 perception tasks, our LiDAR task network is more than 3 times smaller and 6 times faster, showing its high efficiency, which is crucial for online deployment. Then we study the accuracy of LidarMTL compared to single task networks. This table shows that the object detection performance using the standard average precision matrix. The LidarMTL network achieves competitive detection performance compared to other well-performed LiDAR detectors, such as second and point pillars. LidarMTL also works well in the point-wise prediction tasks. For example, for foreground and ground area classification, LidarMTL performs similarly to RangeNet++ and SqueezeSec3.3, which are state-of-the-art networks for LiDAR semantic segmentation. Next, we study the impact of task combinations in LidarMTL on the single task performance. As an example, the figures here report the performance of object detection, foreground classification, and ground height estimation when jointly trained with other tasks. Only small difference has been observed with a variety of task combinations, indicating that LidarMTL is robust against the task combinations. Furthermore, we studied the impact of loss weights in the multitask loss function. This table reports the perception performance for each single task, as well as the average network's ranking, trained by different loss weighting. The networks trained with loss weights from grid search depict visible improvements compared to those without grid search. When combining uncertainty weighting and grid search, the network achieves the best multitask performance. We conclude the necessity of using loss weights with grid search. We also study the robustness of point-wise prediction tasks with increasingly sparse LiDAR points. Evaluating this robustness is crucial for autonomous driving because the sparsity of point cloud varies significantly among LiDAR sensors and vehicle setup, and largely affects the perception performance. In this regard, we use the LidarMTL network trained with the full LiDAR point and make inferences on the evaluation data with downsample LiDAR points by factors 1 up to 32. The figures show that different tasks have different robustness against sparsity. Specifically, the average position or AP scores of foreground classification, drivable area classification, and ground classification remain above 90%, even at a downsample factor of 8, showing the high robustness against LiDAR point sparsity. Finally, we show that LidarMTL can be used for online localization. In this regard, we use a drivable area and foreground predictions from LidarMTL to filter out LiDAR points, which serves as a pre-processing step for localization models. The localization methods achieve smaller root mean squared and higher success rate with the help of semantics provided by LidarMTL. To summarize, this work proposed a LiDAR-based multitask network to jointly perform 6 perception tasks for 3D object detection and road understanding, which were only studied separately in previous works and lacked quantitative analysis. The proposed network achieves competitive accuracies compared to single task networks and is 3 times smaller and 6 times faster. Ablation studies show that the network is robust against the LiDAR point sparsity and the number of tasks, and it provides useful semantics for online deployment. We also show that a proper loss weight setting is important in training the network. In the future, we plan to extend the network to process multiple frames for motion estimation and to fuse with camera images.